So good afternoon, everyone. I'm gonna start here to talk about Clang as a front end. So this talk will be a bit different from the other talks. So this is actually not changing Clang itself, but actually using it. Our agenda, I'll just start by saying why do you need to find bugs, a brief introduction to model checking, ASBMC, the tool that I'm working on, the Clang frontend inside the SBMC, and the future of SMT solvers. So why do we need to find bugs? Does anyone remember this case? Ariane 5 was launched in 1996 and exploded 40 seconds after launch. Does anyone knows why it exploded? What? Yeah, it was an exception thrown by a conversion from a 64-bit float to a 16-bit signed integer, and they just lost the rocket. So in 1996 also, there is this case of USS Yorktown. They automated the whole battleship. And does anyone know why it stopped working, why it broke, why it crashed? So it was a really simple bug. It was a division by 0. And the whole battleship crashed and had to be towed back to the naval base. So yeah, embarrassing, right? So we need to fix bugs. We cannot have those situations happening when you are commanding a battleship, right? So why it's formal methods? Formal methods is a way to try to avoid that, to find bugs. What's the main standard today? It's testing or simulation. So you have a program, and you check a path on the program, and you get an error on AOK. So it checks paths on the program. It may miss some errors, but that's okay. You can check. Since it's quick, it has small memory requirements, time requirements. You can actually check a lot of times, so you get a good coverage. On the other hand, model checking, it's an encoding. So you have the programming specification of the program, and you check all the paths. All the single possible errors are checked by the model checking. And in the end, you have, okay, no bugs, or error trace. So you can actually see the set of assignments that lead to that bug. The problem is, since you're converting the whole program, it can be extremely resource hungry, so memory and time. We are working here at University of Southampton with bounded model checking. So it's kind of a lazy approach to model checking. We bound loops, array size, context switches. So we just keep increasing until we find a bug, or we just say we don't know. It's good to find bugs because usually bugs are really shallow in the program, so we don't have to iterate that much to find bugs. It can never prove that the program does not have bugs. So it will either say there's a bug or I don't know. And if you have infinite loops, it might be a problem because you can never unroll all the program to all the possible paths. So you might never be able to actually check all the possibilities. So ESBMC, it stands for Efficient SMT Based Context Bounded Model Checker. It's this architecture. I'm not going to go into details in each block, but basically we get a source code, a C or C++. We convert to a simple language called go-to language. We basically remove switches, loops, and just make the program simpler. We do a symbolic execution, which is go through all the paths in the code. We encode the constraint in properties of the code. So properties are like if a variable is never 0, if it's a division, this kind of stuff. And then we code it using SMT. Right now we support Z3, Bulactive, Matsat, CVC, and X. And well, this is the whole process. And I'm focused on the Clang frontend. YesBMC has all this built-in verification support. So for pointer safety, array, bound access, and division by zero enabled by default. But we also check overflows, memory leaks, deadlocks, data races. I'll show you a small example. Some more examples. So here are a few examples. Don't mind. Okay. So don't mind the gaps in the program. They are there for a reason. So we just have a function full, and it does in the division. And we want to check all the possible values of A that will trigger a bug in this program. So it's simple as YesBMC. So it will find a set of assignments that will lead to a bug. You see these big numbers there. So we can actually do something like, okay, my program will never have this kind of input. For instance, my program will only have A ranging from 0 to 100. So we can write stuff like, assume that A is between 0 and 100 and B is between 0 and 100. So this is example 2. So it will try to find a property violation that will trigger division by 0 for the values of A inside this range. So you see if you use 5 and 1, this will trigger division by 0 here. This is using Bolecto, one of the solvers. You can actually check for using other solvers, so Zatri, Matsat. So different assignments, but they always trigger the division by 0. This assume is actually the same as if we write an if this condition is not met, just return 0. So it's the same. So finally, this example 3, let's say I don't want to check division by 0, right? You can either disable division by 0 using the flag for the tool, or you just assume here so that C is never 0, and C is the equation for the division, right? So let's say so no bug, right? But I mean, you don't want to check for that bug, right? But let's say you want to check for overflow. You actually get a set of assignments for overflow. You can check with other solvers. That's that as well. Crap. Sorry. Right, so yeah, so these are simple cases, but you can see they're really effective to find those bugs. We have actually the set of assignments that lead to that. So it's easier for the developer to see how he can reproduce it. Another program here with concurrency. So it's basically a program with a deadlock, and we can check that as well. YesBMC tries something very naive when it comes to check concurrent programs. So by default, deadlock is not enabled. So, sorry. So it checks by default if the malloc return a null pointer. But with this flag, we can force it to always succeed. So by default, it doesn't check for deadlock. But if we add the deadlock check, it will eventually find the bug and give you the backtrace for the set of assignments that lead to the backtrace to the deadlock. YesBMC try to interleave all the possible points in the program. So if you have huge concurrent programs, that will take a while to verify. You try to interleave everything.
A quick question: how does it reason to find this deadlock? Just quick explanation.
Okay, so we encode everything using SMT, and it's complicated. We can talk later. Okay? All right. So, okay. So these are simple examples of using SBMC and the Clang frontend, right? Why we are moving to Clang frontend? So our old frontend was about 15 years old, so we didn't have support for a bunch of stuff. So, for instance, compound literals, stuff like this. And, well, I'm not a really good Bison developer, so I had no idea how to implement that. And we didn't have support for designated initializer, stuff like this, to initialize arrays. No support for type-of operator. It was full of bugs, almost 30K locks. So every single...
On your program.
What?
You didn't pass your program on your program. Then you would find all the...
Yeah. Let's talk about that later. So every single change in the program it would lead to a lot of bugs and stuff, and it was hard, especially when I talk about C++. So we tried to, our old frontend tried to support C++ 98. There was hacks everywhere to support them. One of the problems is that we never really understood the rules for template instantiation because they are hard. You're going to see that later. And it extended the C frontend plus 35K logs. So yeah, we don't want to maintain that because that's not the objective of the tool, the main aim of the tool. The tool needs to verify the program. We don't want to maintain that. And then came Clang. Clang has a well-defined AST. So we just actually need to write a converter for the AST from Clang in 2 hours. New features, we just have to add a new conversion node. I will never have to program in flex Bison anymore, so that's alone, it's good. And we have a convenient function like evaluate as integers, evaluate as Boolean conditions inside the Clang that we can simplify a lot of the AST for us. We have warning errors for a real compiler. So the same errors and warnings you get from the compilation you're going to have on the verification tool. And it's much smaller. So just the C front-end is about 4K logs and the C++ about 7K logs. So much easier to support. The C++ front-end is not released yet because we don't have any polymorphism, but I'll talk about that later. And there is another thing that alone by itself, it makes the Clang awesome, which is the AST contain all the instantiated templates. The AST contain all the instantiated templates. Have I told you that the AST contain all the instantiated templates? And I'll show you why this is so great. So I have here the standard. So this is probably the last standard before the release of the C++ 11 standard. So you see there the date. If we go to page 36A. So we are talking about explicit instantiation, right? So that's easy, right? So we have a lot of points, a lot of examples until we get to, no, I'm not on the right one. Where is it? Sorry, explicit instantiation. So we get to the point number 7 here. And I'll read for you guys. Is it?
Yeah.
Sorry, here. So a placement of explicit specialization declaration for function templates, class templates, member function of class templates, static def members of class templates, member class of class templates, member class templates of class templates, member function templates of class templates, member function of member templates of class templates, member function of member templates of non-template classes, member function templates of member class of class templates, etc. And the placement of the partial specialization declaration of class templates, member class templates of non-template classes, member class templates of class templates, etc. can affect whether a program is well formed according to the relative positioning of the explicit specialization declaration at their point of instantiations in the translation unit as specified above or below. When writing specialization, be careful about the location and make it compile will be such as river or kindle itself immolation. So it's hard, right? We don't have to deal with that anymore. Clever people done that for us on Clang, so we're just going to use that.
They also removed this bit from the C++ 14.
Really? Oh, that's much better there. So why moving to Clang? We are using libtooling because by the time we tried to use the libclang, there was some functionalities. I think it's much better now, but since we started with that, we are not moving back again. Most of the code to walk the S2 is based on the code in stdumper, type printer, and the code in libcodegen. Some limitations we found is C++, for instance, does not support implicit function declarations. So yes, BMC assumed that I showed you guys we're not going to work by default. I'm still trying to work out how to fix that. Some random crashes. For instance, if you try to get a line number from translation unit in Clang 3.6, it crashed, but it's fixed since then. Clang does not build the table for you, so at least not using the defined AST, so I'm going to have to write another converter for that. We have no access to the static analyzer. That would be excellent for us, since we're trying to verify the program, try to get some information about the reasoning of the program. There are no optimizations at the AST level, which is that's reasonable because all the optimizations are done at bytecode at LVM, so we get small optimizations. And there are some lack of documentation, some corner cases. For instance, let me show you guys this. So that's a small example. We just have a class X, and we do a copy constructor, right? We call a copy constructor. And if we try to generate the AST for that. So briefly, this is the brief variables I0, I1, I2 of the member function, the member str. So basically what Clang is telling me here is that this is the copy constructor for this class. And I have no idea where this is coming from. And Clang does not tell me either. So however, by the time you reach the code gen and when the bytecode is generated, just a main copy for that case in particular, but there is no documentation for that. We just try to pass the AST when we see that, and there is no explanation why that is like that. Right?
I think there's just placeholders to generate some IR
exactly.
That will match to an M-copy.
Yeah. But the thing is, we are very careful when it comes to variables. And if there is a variable without declaration, we don't like it. So we just don't know what to do. So,
is there any difference between the declaration of those variables and the declaration of any other variable that you have in the context? Because if there isn't, then those could be real variables. And then global variables, and you have no idea if it's a real thing or it's just a made up.
Exactly. Well, we don't have any idea how to do that. Okay. So just a bit future about SMT solvers. So why we don't check our base code? Because SMT solvers are really resource hungry. We're talking about hundreds of gigabytes to formally verify auto. And this is, well, SMT solvers are evolving, but they still need a long way to go. But what's the future for them? So going mainstream. So this is a series of patches by Dominic Chen. They are on the Fabricator. they add Z3 to the constraint solver. The memory usage is about 20% higher, which is okay. However, the time to run is about 15 times higher. So that's something to improve. But we are getting there. With the Z3 patches, we are able to finally reason about symbolic float expressions that the static analyzer could not do before that. It's not accepted to mainstream yet, but it's being under active discussions on the fabricator. And that's it. SBMC is open source. It's closed development, however, for some reason, our developers are shy, I guess. And please check the code, and any reason, just send me any question, just send me an email later. Thank you. Have any question? Yep.
You mentioned that it doesn't do root tables. Are there any other notable constraints about the kind of code that you can analyze?
Not really. Not really.
Repeat the question.
Okay. So he asked if there's any other limitation other than vtable for the C++. Not really. Everything else it's there. We just have to parse it. Actually.
So even like function pointers and things like that you can follow?
Yeah, yeah. I mean, not on the AST, but...
But wouldn't you have to track like all the things that could be theoretically loaded into that function pointer, which is also an analysis?
Yes, this is done inside SBMC on a later step, not on the AST. So the AST is basically just to convert that to our internal representation. So we don't have to pass the program, do any kind of type check.
Okay, cool.
Right?
What language is SBMC implemented?
So it's in C++. Yeah, C++ 11 basically.
So it wasn't a big deal to use C++ APIs from Clang?
No. Yeah, basically C++. We have some Magpie developers. So Magpie is that bird that likes to steal shiny things. So every new shiny things, new features on C++, we just like to implement that. So soon we're going to be moving to C++ 14. Okay?
What is the biggest software project you did check with your tool?
So he asked about what's the biggest program we checked. In terms of source code, about 10 megabytes of source code, which is small to medium, I guess. It really depends on the program, because a lot of stuff we can just throw away and not give it to the solver. We do some kind of static analysis on the program later on to remove unreachable path and that kind of stuff. So it really depends on the program, but so far about 10 megabytes of source code.
Have you run it on your own program?
Oh, what?
Have you run it on your own program?
On the tool? Not really, because it's too big. Yeah. Yeah.
Can you state the difference between this tool and CBMC? Because you're using C++.
So yeah,
Is that
so
technology the same?
SBMC is a fork of CBMC, and CBMC is mostly about set solvers. It does have support for SMT solvers, but it's less than ideal. We are focused on SMT solvers. Yep.
There are also other tools that could make B, for example. What is the advantage of using your tool versus B, and what are the disadvantages?
So CLI, as far as I know, it tries to run the program and generate coverage, right?
No, not really. It's a component. It's a symbolic execution as well.
Okay.
So it tries to produce all the possible input for the program to cover all the possible path.
Mm-hmm.
While you, as I have seen, do some kind of forcing them to produce some kind of path.
Yeah, so what's the difference between CLI and SBMC? So we walk all the paths, or do the symbolic execution, and we do a bounded check. So you actually can define how many loop iterations do you want to run, and we call SMT solve. I don't know if CLI uses SMT solve. Yeah, so yeah, I would say the bounded model checking. It's the difference. You can bound the verification. Right?
Thanks for the talk. So your tool can verify deadlocks and stuff like that.
Yeah.
Can you also verify arbitrary things that you express using LTL or maybe something else?
Yes.
And then how
Yeah.
expressive is your
Yeah,
specification?
we have a support for ETL. There is a paper we published 4 years ago, I guess, that define all the semantics for that. You just have to write in using LTL on the function calls, I guess.
And you have CTL or mu calculus or
LTL only. Yeah.
LTL.
Yeah. Yep.
How do you go about modeling sort of system library? So I mean, if you're using Clang, that's getting in.
Yeah. So.
File that you don't have like Unity.
Yes. Okay. So for C++, it's not a big deal because they provide the whole code. But for C, stuff like string, printf, this kind of stuff, we have a model for that internally. It doesn't cover all the C libraries, but most of them are there. So handling strings, chars, files, everything is there. Floating points as well. Yes?
So you start from the Clang AST. Could you comment on why you didn't choose to start from the Clang CFG? There's also a CFG.
Because basically, by the time we were looking at the Clang, we thought that the ST will provide the most information we needed for the verification. So the CFG can come kind of optimized. Some branches can be cut, and we just wanted the actual representation of the program, which is bad because the CFG code kind of generated the vtable for you, right?
Yes.
So,
This
yeah.
what you mentioned the drawbacks in the Clang.
Yeah. Yeah.
And also, sorry,
Yes.
another place where you could have flagged this up is that the LLVM bitcode.
Yes, there is a tool that does that. It's called SMAC. So it works from the bytecode and converts to a boogie language, I think that is, and try to verify. Yeah, the advantages of that is that you can verify much more language, not only C and C++, right? You're working at the LLVM bytecode. But since we are focused on C and C++, we decided just go with Clang. Yep. Okay, thank you very much.